All right, I wanted to look through another example of the value being beyond what our table will use. And I want to do this with the other z formula we're using to show that it doesn't depend upon which z formula we're working with. It depends upon what the z-score computes to be. And so for this example, we're going to use mu is equal to 73.3. We're going to use sigma is equal to 6.3. We suppose we take a sample of size 44. Do we see this is sufficiently large? All right, the sufficiently large standard is met one of two ways. Either the value is 30 or more, in which case you're good to go no matter what, or if the phrase assume the population is normally distributed, then you're good to go no matter what. So in our case, n is equal to 44, so we're good to go with sufficiently large. And suppose we wish to find the probability that x is greater than 77.2. All right? We take a sample of size 44 from a population with mu equals 73.3, sigma equals 6.3, and I've written this incorrectly. We want to find the probability that x bar, the average of the sample, the mean of the sample, is greater than 77.2. As soon as we see x bar here, and as soon as we see this sample, that's sort of the double indicator that in our picture, yes, this is the z-scale, it always is. But this scale is the x bar scale. As soon as we know this is the x bar scale, we know we're using this formula for the z-score. Z is x bar minus mu over sigma over square root of n. And again, if you're very good, if you're adept at using parentheses, you can put parentheses around numerator and denominator for your calculator. If you're not quite sure of yourself with the parentheses, then you can use compute the numerator, hit equals, write it down. Compute denominator, hit equals, write it down, and then just divide. And if you do that, your round off error may be larger, but I will not penalize you for that reason. All right? So let's see if we can compute this. The center is mean, which is 73.3. Standard deviation is 6.3. And we want to find the probability x is bigger than 77, which is located here to the right, 77.2. We want everything greater than. So greater than means we shade this piece. But when we so that means this, what we want here, we're looking for this shaded area. These must match up all the time. But the arrow always goes left. Since the arrow does not match this region, that means when we find this table value, we need to do some arithmetic. All right, so here we go. Z is x bar minus mu over sigma over square root of n. So in our case, x bar is the 77.2 minus mu 73.3 over the standard deviation is 6.3, and the square root of 44 comprises this denominator. And now we need a z-score. And so I have 77.2 minus 73.3. I'm going to close that, divide that by, open 6.3 divided by the square root of 44, close. And I have, this is approximately it's 1062. I'm going to use 4.11 as my value. So the z-score is 4.11. From that, we compute the table value. Not compute. We're going to find the table value in our table. But as we saw in the previous example, our z-score of 4.11 is beyond what this table will afford. And our rule is anything beyond the 3.49 limit, we will use a table value of 0.9999. And so our table value, 0.9999, that value goes on the arrow, all right, which is the region we do not want. We want everything else. So the probability that the mean is greater than 77.2 is given by 1, subtract off the piece we don't want, and that's 0.0001. So if the value goes beyond the edge of the table, we will use the 0.9999 none for the large, and if on the other end of the table, we would use the 0.0001, and that value is used no matter which Z formula we use. It's independent of which Z form. Well, all that matters is when you get the Z value, if it's beyond the table, we'll use the two limiting values, and that's the way that we will handle that in our course.